Give me a sec and I will begin sharing my screen. Okay, cool. And then I'm gonna have this open. Okay. It should be like, yes, perfect, okay. I was re-downloading the code because obviously we can't show the people the answers. So I was downloading a fresh copy. But yeah, so I guess welcome to Recitation, or welcome to the bootcamp, everybody. So we're mainly going to cover homework 1 part 1 today. We're going to talk a little bit about homework 1 part 2, but you know, there's a lot of resources for very similar problems online, and then also the assignment hasn't really changed that much from last semester. So we figure you guys probably have a good shot at finishing that already. I mean, obviously it's still challenging, but it's a lot less, I guess, confusing and like a lot more public, I guess, in terms of how many resources are available. So today we're going to mainly talk about homework 1 part 1. So again, if you guys haven't filled out the form that we posted in the Piazza thread, if you can fill that out, that would be great. We'll also go over the results in a bit. But I guess sort of the game plan for what we're going to do today is we're going to start by, I guess, going over the deadlines that are upcoming, and then sort of giving you guys like a recommendation for how to approach things, like, and then also, I guess sort of, yeah, actually that's pretty much it. Just give you guys a game plan for how to approach everything. And so after that, we're going to talk about homework 1 part 1. We're basically going to kind of go over things in order, but how we're going to do it is we're not going to like basically just read out the write-up, because that will not be helpful. What we're going to do is we're going to, at each section or like each page, including the problems as well, we're pretty much going to stop and then say, like, we're pretty much going to give like an overview of what that page or section is talking about. And then we're going to ask, we're going to open up to questions like pretty quickly so that people can ask like any sort of doubts that they have on these parts. And so after that, we're going to, I guess, sort of walk through, let's see, walk through some code. Specifically, we're going to look at an implementation of an operation. It's not going to be a new operation because that would be basically giving you an answer, but we're going to help explain like what each decision is and like computationally what it's doing and mathematically what it's doing as well. And so if anything, it should make really, really clear what the other operations will be like. So it should be helpful as well. And then I guess, yeah. And then after we finish homework 1 part 1 discussions, we'll have some general questions, and then we'll talk a little bit about homework 1 part 2. And then afterwards, if there's time, we're trying to aim to not have this go over an hour. But afterwards, if there's time, we'll, I guess, open questions about homework 1 part 2 as well. So that is the game plan for today. I guess any questions, comments, suggestions, things that you guys would like to have done, et cetera, et cetera. If not.
In chat, so I guess you can go ahead.
Yeah, perfect. All right, so let me share my screen. Oh, and also let's open up the survey results as well. Yeah, this is going to be a little informal, FYI, but hopefully it's still helpful. So the survey is anonymous. Let me try to get some graphics displaying how people responded. Okay, I think this should be safe to show. Yeah, this is safe to show. I will share my screen with everybody. Share. Okay, can everyone see, I guess, sort of the Google form page? Yes?
Yep, it's visible.
Okay, cool. All right, so these are the responses. So I guess people have a range but mixed feelings about finishing the homework in time. Hopefully this should help today, and live updates. So it doesn't seem like it's awfully terrible. Like if it was like all over here, then that would be truly horrible. But for the people who are feeling a little bit less confident, we will try to help you today. Okay, good. Most people read the write-up. Okay, most people feel okay about the write-up as well. Wow, this is a crazy neat curve, holy crap. And then, did you read the write-up before starting the code? Most people, yes, fantastic. And then few 6 people, shame on you, but also whatever. Okay, so it seems like, so this is in order. Yeah, this is in order. So it seems like most people haven't started yet. Okay, so that's good to know. A lot of people working on operations, and then it slowly sort of peters out. Yeah, this is kind of what I expected in the sense that linear layer, because of broadcasting, is going to be a little challenging. And then Autograd engine, just because it sort of like incorporates everything together, is also going to be a little bit challenging as well. Yeah, I believe the meeting is being recorded. So yeah. Okay, and then what sections would you like to have covered? This pretty much means everything, I guess, from what I'm interpreting. So yeah, we will be covering that. Tensor dot backwards, interesting. Okay. Okay. And then concepts understanding. This is IC 47. Okay, perfect. So yeah, I guess we'll get started now. So let me pull up the write-up. All right, so here's the write-up. Oh, also a note. So we've been making a couple updates to the write-up throughout the week. And so I think so far there's been like pretty much one update where it affects the code a little bit. And that's during MNIST, where it seems like not a whole lot of people were at this point. So hopefully it hasn't affected you yet. But I would re-download the write-up just so you can like have the most updated instructions. So we're supposed to construct a change log. That's on me. I actually haven't done it yet. I've had a lot of other work, mostly IDEO related. And so I will get to that straight after this meeting, I promise. And so, but yeah, basically the write-up has changed a little bit from the initial release. So make sure to re-download that. So I guess a summary of this section is basically that you're implementing a version of PyTorch that has Autograd in it. Last semester's, like basically what it looked like is people were implementing very similar like network components, but then they would implement a specific backwards for every sort of component. Whereas for this one, you're implementing a backwards for smaller operations and also like some functions if you choose to do it that way as well. And so it's a little bit confusing, but then it actually ends up being a lot easier once you have these operations made. And so down the line, hopefully it should be a little bit easier. Yeah, so this is the structure. Just a note, we got a couple questions on sandbox.py. So this is for you just to like test things out. This part, the sandbox.py is not actually graded, so you don't have to use it at all if you don't want to. We recommend that you do though, because it's really easy to debug in there and then make sure you're not, like breaking components, that kind of thing. And so sandbox.py, again, is completely optional. So yeah, that's pretty much all there is in this page. Oh yeah, so another thing is object-oriented programming. If you guys don't know what that term is, yeah, I'd probably Google it. But I'll also share a link. Actually, I have the link. Let me try to share it in the chat really quick. But if you're new to object-oriented programming, I have a link from CMU actually, where they basically just have like a walkthrough of what it is and how it's sort of relevant in Python. Oh, and I flipped the colors black and white. I forgot that. I forgot that I'm an all dark mode kind of person. So yeah, and if anyone wants to know how to flip PDF colors, just let me know because that's my game. All right, so this is in the proper color, blah, blah, blah. Okay, so we're gonna, I guess, sort of lightly go over Autograd, and then we'll stop and take conceptual questions because it seems like there's a decent number of people who have those. And so I guess basically the gist of this page is that, as I mentioned before, Autograd basically lets you implement simpler operations, the backwards for that instead of re-implementing stuff over and over. It basically modifies forward propagation and back propagation. And then the other stuff is mostly similar, but yeah. And over here, this is basically just saying like what backprop does in general is basically trace the influence of each weight on the loss value because you're trying to minimize it. And yes, the recording will be available. But yeah, so I guess any questions on this like sort of intro section initially? Okay, so feel free to post in the chat as well. There's like a bunch of TAs here today, and so we can help answer those. But yeah, and so basically during the forward pass, Antti has like a really good like visualization of this in the recitation 2 yesterday. And so what happens during the forward pass is basically this graph is constructed sort of as operations occur. And what this graph does is it basically tracks how like input variables, how variables are affected, which basically allows you to basically trace things back during the backpropagation process. And so, yeah, so this section specifically talks about function.apply, which is actually a later question, but it's very, very important for the forward pass. And so what I will say is this is essentially pseudocode. Like it's very, very close to what, like the final thing that you're going to be implementing. There's basically just like a couple of if statements that you need to do, but that requires an understanding of the node types. And these 2 steps, I believe we've already done for you. So yes, we've already done these 2 steps, and it's these 3 that you need to do. So any questions on that, I guess initially? There's a couple of people in office hours who asked stuff. So somebody asked in the chat, are tensor and node the same thing? So tensor and node are not necessary, so they're not the same thing, at least in the code implementation. And so tensors are objects in and of themselves, and they actually hold node objects. So they're different things. But yeah. Hopefully that answers that question. Yeah, so that's that topic.
In terms of like the actual neural network, I'm started like not understanding like what is that like addition and subtraction, division, like what does that actually mean in terms of the network and like how it's being trained? Like how do we tie this graph back to that?
Yeah, so in within the neural network itself, so like if you were thinking about like a PyTorch sort of implementation of a network, you have like linear layers, batch norm layers, like, you know, maybe convolutional layers, something like that. Within each of those layers, there are a bunch of different operations occurring, right? And so really what these sort of add, you know, subtract, all these operations are doing is it's basically zooming in really close and saying like, okay, as part of a linear layer, you're adding, you know, mx plus b, and so mx, like, I mean, those 2 terms being added together. That's what's actually like a node in this implementation, if that makes sense. And so it's pretty abstract in a sense because all nodes are just kind of treated equally in a sense. But yeah, does that answer your question?
So like would this whole graph represent just like one perceptron or something?
No. So if you looked at, so it would basically be the entire graph is basically the entire forward pass of a neural network. Yeah.
Okay.
And so this is very tiny, but like an actual neural network would have like a ridiculous number of nodes. It's like, you know, any, I guess, sort of modern neural network. I think it's probably safe to say like hundreds of thousands, like millions. Is that safe to say? Yeah, so it'll be very, very big is the conclusion. But yeah, so.
You can say that it's a toy example for now, the graph.
Yeah. Okay. So, yeah, so one thing that came up a lot during office hours was like the creation of nodes and like how that's handled and stuff like that. That's basically going to be handled in function.apply. And what I will say about that is pay attention to this, like, right, so this paragraph, I feel like, explains it pretty clearly. I guess if there's any additional or specific questions on that, you guys can ask or come to office hours, but yeah, I did get a bunch of questions about that during office hours. So I guess moving forward, yep, this is just basically the forward pass. Remember, we're trying to get derivatives. backward pass. Hopefully people understood this description. This is actually like a really crazy fact where like every computable function is a DAD. And so that's kind of like the crux of what I guess Autograd is doing, is it's basically doing a graph traversal, and you can do it for any possible function, which is, you know, a crazy fact. And so that's that. So I'm seeing some questions in the chat. I see there's an earlier question about what nodes refer to. So that will actually come later in the write-up. And in fact, in the appendix as well, there's like a pretty clear description of what nodes actually are. Let me find it. Here, these are the nodes. They're specific object types. And a tensor will store these types of nodes. And just note that constant is not a type of, like, it's not an explicit object. We just store none, and that's basically a constant code. So just keep that in mind. Okay, so going back, let's keep moving. So yeah, we basically go through the steps. So just a note on, I believe it was tensor.backward. I saw a couple of people had wanted to cover that topic. Tensor.backward quite literally just does this. So if you implement something very, very similar to this, like where you're basically just making a new tensor full of ones and then passing it to that function, you'll pretty much pass like that part. So that's what I'll say. Is like, don't overthink it. It's essentially one line of code. And so, yeah, that's that part. And so this pretty much begins like the sort of recursive calls. Like if you guys watched Recitation 2 yesterday, I showed you guys an example of like calling a recursive function and how it sort of intuitively kind of looks going down and then going back up again. And so this would be like the very first call. That's how you can think of it. Yeah, and so within the first call, you begin the DFS, where also that code we showed you guys in Recitation 2 yesterday for like the branching recursive function is very, very similar to what you're going to be implementing for here. So like, just keep that in mind, it's a pretty big hint. And so, yep, we're doing the first recursive call. This is a little bit difficult to walk through. Was there anyone who's particularly confused by like how, like what order things are happening within sort of the backward function? If so, we can talk about it, but I may save that for you guys to sort of review, because I'm hoping this part is pretty explicit. But yeah. Okay. Okay, so I would like to know the order. Okay, so essentially what happens is you receive the inputs. Basically, the inputs are going to be, might help to show the code. I'll try to cover this quickly. Let's see. All right, so this is the backward function as you guys will have it. So this is grad function. This is essentially like the node from the tensor, sorry. Yeah, this is essentially a node that you're receiving. And the node basically has, all it contains basically is instructions for how to modify gradients, or instructions for how to compute gradients / pass them on / modify them, like basically that. And then, so the second input would be grad of output, where this is basically a tensor. This is basically the gradient that you're passing along. And so when we say like back propagation, you're basically propagating these gradients sort of backwards through. And so this would be the gradient itself that you're passing. And then the grad function again would be the instructions with what to do with this gradient. And so within here, basically this ordering covers it pretty well. But first things first is you actually need to calculate sort of what the new gradient will be. What that means is basically when you do a dot apply with grad function, it should handle, like if you do dot apply and then plug in the gradient of outputs, like the second term here, it should basically handle the calculation for you. And then over here is basically where you're doing the recursion thing, which is again, very similar to what I showed you guys in Recitation 2. So there's really only two things that you need to do, and the ordering is pretty clear here. And so hopefully that answers the question, but yeah. And let us know if not. But yeah, so that is basically that explanation. And this just walks through basically a bunch of the edge cases, things that are, I guess, needed. So someone sent me a private message, I guess maybe send to another TA for now. And then, yeah, that would be good. Other TAs are, I guess, Jin Hyung, David Park, and then there's also Antioch, Auntie, and Reshmi, and I believe I saw Mia in her earlier, and Tony, I believe I saw as well. Yeah, so a lot of other TAs here, just send them a message, but yeah. So next, storing a gradient. Oh, so a lot of people had questions about storing gradients. Accumulate grad basically handles all of it for you. So you shouldn't need to do a plus equals operation yourself anywhere. Pretty much, yeah, I believe that's true. Yeah, you shouldn't need to do it yourself. This node will handle it all for you, and we've already implemented it. So when you do the dot apply with accumulate grad, it'll handle it for you. That's it.
Jacob,
yeah.
there are a couple questions on asking to apply, asking to explain apply in detail. Also the arguments for apply.
Yes, okay, I can do that. So dot apply, so so there's kind of a blessing and a curse where dot apply, okay, so I'll explain it. So there's two node type implementations on this code file. And it's a little bit unfortunate that they're separated. But one of them is accumulate grad, and the other one is backward function. So these are two of the three possible node types. And they both have a method called dot apply. Def apply, and then def apply. And there's a very specific reason for why that's the case. It's because over here, you're receiving the nodes, right? The grad function. So when you call dot apply on this node, there's an implementation of dot apply on both of those objects. And so what essentially happens is it, based on the node type, it runs the correct set of instructions for what needs to happen to that gradient, if that makes sense. And so for backward function, I'll cover that first. For backward function, what it's calling over here in dot apply, okay, so really quickly, I'll explain what these args are. So when it says star args, basically it's receiving a variable number of arguments. And so like, you know, for instance, I'm trying to think. Normally with functions in Python, you have like arguments that are separated by commas. Star args basically says like, you can have a variable number of these arguments and it'll just pass them straight through to over here. So that's basically what that means. Some people have some questions. Whoa, there's a lot of questions. Okay. And so TAs can help me, but I'll keep going with my explanation. So that's, so in backward function, it's basically passing these arguments to the operations.backward. And so if I go to functional.py, so you'll notice in a lot of these operations, for instance, in add, the operation itself has a backward thing where the gradients are being calculated. And so what that means is if you actually look at the write-up, in the steps where, oh, this is the black and white one, sorry, or black one, sorry. Yeah, so whenever we have these calculations over here, the operations.backwards is handling these for you. So hopefully that explains that. So when you call backwards function, it'll basically perform this, yeah, when you call backward function.apply, it'll basically handle this for you, if that makes sense. And then, yeah, so going back. So I saw that someone wanted me to explain, okay, actually let me cover accumulate grad first. So this is the other sort of active node type, like set of instructions that might be applied. So this is a case where you have like a gradient enabled leaf tensor, which is essentially like, you can think of it as like the last sort of stop. Like if you had sort of, let me pull up the visualization, or actually let me draw it on the screen. Annotate. Hopefully this is clear. Let me know if not. So if you had like a graph that looked like this, And let's say that like this node over here was the loss that you're backpropagating from. Like a gradient enabled leaf tensor would be like this. It's like the last stop, and also it's gradient enabled. If it's not gradient enabled, then it wouldn't be accumulate grad. It has to be gradient enabled and also a leaf tensor, basically the last stop on a chain. But yeah, so hopefully that explains that. So accumulate grad is basically like, you know, you're at the last stop, so you're basically storing the gradients. The description in the write-up should be pretty clear as to what that means. In fact, I wrote two long pages about it, or I guess 2 long pages, but yeah. This explanation is exactly what's happening. Is you're basically just constructing this term by term. And so every time that, you know, every time that a path goes back to that leaf tensor, it's basically a single term here. And when you do a plus equals, you're basically sort of iteratively building this term up. That's essentially what's happening. There's a lot of questions. Okay. Yep, and someone also asked about context manager as well. I'll also explain that. Yeah, I'll also explain that. And so remember that in the forward pass and the backwards pass are happening at different points in time. Like the forward pass happens first and then the backward pass happens. In the forward pass, there's a lot of concepts to explain. Let's see. I don't know how else to explain it. Context manager is basically like passing things between the forward and backward pass. Like that's pretty much the only thing that it does. It has a single method saved for backwards. This is meant to save any tensors that you receive, because normally what we want to do is store the input tensors during backwards, the input tensors to that operation. And so, yeah, so it essentially stores tensors within the context object, and that object gets passed to that operation during both the forward and the backwards. So in effect, you get access to the same objects during the forward and the backwards, because you'll probably need them, is the thing. So that is essentially that. With respect to the context manager, when and why do you need to take the first element of a list, for example, in log, when pulling it in backwards? Why is it a list, not the tensor covered? Why would we take the first element of a list? Let me look at log, because that's what they're asking about.
I can talk about that. Basically, you save, if I'm understanding your question correctly, when you save things in the context manager, you get back a list of the things you saved, and you just use whatever you saved. So if you want everything in the list, you just take the whole list. But I think in context of log, you only need one thing that you saved. And you could totally just save that one thing. So it's just up to you.
Yeah. And so somebody asked in the chat, and this is actually a really good question. They're asking, so in the write-up, if a node is backward function object, it says pass gradients. If a node is a backward function, the write-up says to pass gradients only if requires grad is equal to true. But how do you access the requires grad property? So the thing is you don't actually need to access the requires grad property during the backward pass. And so, yeah, so specifically it would be during this part where you're sort of back propagating through. And the reason you don't actually need to access that property is because these objects were created based on those properties in the first place. And so sort of implicitly, if you're given a backward function, you know that, you know, required grad is equal to true, but it's also not a leaf tensor. Like, you know that that's going to be the case because that's the object that you were given. And then with accumulate grad, you know that requires grad is equal to true, and you also know that it's a leaf tensor. And so implicitly, those variables like don't need to be accessed, if that makes sense, because the object itself tells you what that variable, what those variables actually were. Cool. Seems like that answered the question. And so, going back to the write-up, hopefully I'm making good time. Let me know if I'm going too slow, I guess audience and other TAs and stuff. So yeah, actually, where was I? Oh, so I explained context manager. Also explained this stuff as well.
Jacob, someone has raised a hand.
Oh yeah, sure.
Hi, I have a question. So when so almost all the classes in the functional PY, they they inherit the function, that class, right? And the function will just call the apply function, and the apply function will call the forward function
That's right.
of
Yeah.
the. Okay, and the backward function in the Autograd engine.py will just call all the backward, or they just call all the apply function of the nodes, and the apply function will call the backward nodes. Am I right?
Yes, that is painfully correct. Yeah, and
Okay,
that's
got
what I
it.
meant earlier when I said it's a blessing and a curse, in the sense that, like, for some reason, I don't know why, but they also named .apply like the same name in function, even though this is the forward pass one. So I don't know why they've done that, but I guess that's the case. But yeah, so, sorry if I interrupted, but yeah. So hopefully that answers that question. So somebody's asking, is it possible to draw a diagram and illustrate which functions and classes go where? Yeah, that's a complicated ask. I'll have to, let me think. It's complicated because they're so interconnected is the issue. Like if, for instance, if I tried to explain where tensor goes in everything. So it's like, how would I explain where exactly that's happening? I think part of what would help is if you follow the order of the questions that what they're going through, like you shouldn't have any sort of conflicts with, in terms of ordering or calling the right objects. In fact, I think we pretty much always tell you, right, and someone else also said there's a file structure. I think we pretty much always tell you what objects and functions that you'll need. And so hopefully it's unambiguous in that sense. This is the kind of thing where you just kind of need to go through yourself and build an intuition for it, I think, because the diagram would be very high dimensional. I have no idea how to draw it.
One thing I can say is the main thing I think you need to juggle is function versus backward function. And then we posted a note on Piazza with the video explaining Autograd. We found this video a few days ago, and it basically goes over in like pictorial detail, like all the different moving components of this of Autograd. So I strongly recommend you check it out. It's like maybe 10 minutes long, and the first 5 minutes are especially really good. So that visualization is really, really good. So I really think you should look into it.
Cool. Yeah, that's a very good point. Yeah, that video is very strong. So I think I can show you what the Piazza thread is. It's this Piazza thread. It's basically saying helpful resources, how Autograd works.
We can't see it. Oh, there, never mind.
There we go. So this link basically is what you want to click on. And I'll briefly show you what the graph looks like so you get a sense, but I won't spend too long on this. And I don't want to listen to this guy. Even though he's a very good speaker, but I just, not in the mood for it. But yeah, like this will give you a sense of, he does a really good job of showing you how things are interconnected, like how these arrows are and what the edges actually have the symbols on them, like that kind of thing. So hopefully that will help. And yes, and thank you for sharing the link. That's very useful. But yeah. Okay, so that's pretty much like most things in Autograd actually. So if you got through this and you weren't too confused, that's a pretty good sign, I would say. So yeah, I guess any sort of remaining lingering conceptual questions, maybe even on this math as well. Oh, and also any questions about object-oriented stuff, even though we'll talk about that a little bit more, because this is a good time for it now. Yeah, if not.
Jacob, one Chuan who has a question in the chat.
Okay. So someone says, why does Autograd step 1 say that without storing, event passes without storing, it's created the graph traversal method? Yeah. So in step 1 of the backward pass, so that would be this one. So again, this is tensor.backward that we're in right now. So it says in this sentence over here, it then passes without storing this gradient that it just generated to the graph traversal method. So we don't store it because, I mean, by definition, it's the last node in the graph, and you wouldn't need to accumulate gradient there. And so you just pass it to sort of begin the traversal process, if that makes sense. And so when I say storing, I mean using accumulate grad. Basically, that's what that means. So, okay, cool. And then I saw that 2 people raised their hands. Is that right? So can one of the TAs, I guess, call on somebody?
Sure, Jeff. Jeff, you can unmute and ask.
Oh yeah, so can you go to page 11?
Yes, I can go to page 11. Yep.
Yeah, so the example here is really simple, but I have a question about the operation multiply,
Okay.
calculating gradient that goes into, so basically DEDB, DEDA. So I wasn't sure how to calculate that with the shapes. So like, for example, if you look in the graph in page 11 with the example, yeah, so if, let's say A is shape of 2, 3, and B is like 3, 2, then operation multiply gives you 2 by 2, right?
Right, so that's a good question. I realized it wasn't specified in the write-up. Someone actually asked this in FAQ, but this is an element-wise multiplication, at least in this example.
Oh, okay.
In the, yeah, so.
It's not matrix multiplication, it's just element-wise multiplication?
Right, so at least for this question specifically, multiply, it's gonna be element-wise. We should have specified that.
Oh, okay.
But later you actually will, is that giving away a spoiler? It might be, no, it's not a spoiler. You're pretty much gonna need to implement the matrix multiplication that you were talking about over here.
Oh, okay, that makes sense. Thank you.
And that'll be a can of worms, so we'll get to that. And then another person raised hand.
I have the same question. You've already answered this.
Okay. And wow, we are 40 minutes in, holy cow. So shapes must be equivalent, yes. With respect to SGD step, we do not add this to the comp graph. However, we're previously overloaded some required operations and assumptions. That's an excellent question. So someone's asking, when we're in the step phase, which is the 3rd phase after backprop, we're not supposed to add to the comp graph because the gradients have already been established, right? So it'd be this stage. But we've also overloaded these operators for tensors. And so if we continue to like use the operators, then they would probably add to the comp graph, right? And that is true. So what we do is we actually, as you suggested, use NumPy. And so you'd say like, tensor.data plus tensor.data to do an addition, I guess. And so that would avoid adding to the comp graph, essentially. Yep. So hopefully that answers that question. And yeah, so now we're gonna get to the basic operations. I guess I asked David to show implementing add, and hopefully maybe, I guess depending on the time, David, maybe you can, you can either implement it or just like walk through line by line and explain it. I guess it's sort of up to you. But
Okay.
the reason we want to do this is because all of these operations are very, very similar. Like if you understand why like each line of add is the way that it is, you'll understand everything else. This is essentially what I'm going to say. But yeah, I will hand it over to David.
All right. So we'll go over add because this is what you're given and it's a good example to reference while you implement the other functions. So let's see here. So just like any other function, add has a forward component and a backward component. And the forward component is responsible for taking in the inputs and generating output with respect to the function. So in this case, it would add the 2 tensors and just do a plus b equals c and return c. In backwards, you'll be given the gradient with respect to c, and you'll have to propagate it to the inputs. And one thing, actually, I'll talk more about this when we get to backward, but let's go through the forward first. So there's a couple lines of code here, just to make sure that the two tensors are of the same shape and the two inputs are indeed tensors. So you'll likely be deleting these lines of code when you need to implement broadcasting or like adding between tensors of different shapes, maybe even a tensor and a scalar and so on. But for now, we're enforcing that A and B have to be tensors of the same shape. And in the backward pass, so in the backward pass, we'll need information about the inputs. I guess I'll mention it now. So one invariant, or one thing that you always need to maintain for whatever function you write is...
David, really quick, sorry to interrupt.
Yeah.
Someone's asking if you can increase the font size in the code.
I actually have no clue how to do that. Let me just try changing something. All right. Hope this is large enough. Yeah, okay. Right, so one thing you need to keep in mind, regardless of what function you implement, is that for the backwards, so let's see if I can draw here. Annotate, draw. And Jacob, can you let me know when you think I'm taking too long or when I should speed up?
Yeah, for sure.
So backward is going to take in the gradient with respect to the output of the forward, and then it's going to return two tensors, or it's going to return a number of outputs. And two things here. One, the number of outputs of the backward need to be exactly the same number as the number of inputs. And you see that add takes in two inputs here, A and B. So the two gradients returned by backward are the gradients of A and the gradients of B. And the other thing you need to remember is that the two outputs, so the two output tensors need to be of the exact same shape as the input tensors. Again, so the first output of backward is the gradient of A, and the gradient of A needs to be exactly the same size as A itself. And the same goes for B. And as long as you keep that in mind, the other functions, well, they all need to respect this rule, and hopefully that guides your code a little bit. Now, to go back to the code. So since we're enforcing that the outputs of the backward function are of the same shape as the inputs, we save the two tensors A and B. So we know for the backward that we know what shapes the outputs need to be for the backward. Requires grad. So the appendix talks a lot about this, but then basically we want C to require grad if either A or B requires grad. So if A or B wants their own gradients, and then we need to give them their gradients. And if C requires grad false, there's no way for gradients to get back through C to A and B. So if either A or B wants gradients, C also needs gradients. And for actually computing C equals A data plus B data, and that's just simple addition, element-wise addition. Requires grad as explained here, and then isLeaf is the opposite, requires grad. I won't go through the specifics of isLeaf here because explaining what isLeaf is will take a lot of time in general, but the appendix has a really good explanation on what isLeaf is, and the video attached in Piazza also has one. And then you just return C. Now for backwards, you're going to get a grad output input, which is essentially the gradient of C with respect to whatever you called backwards on. And this will be the exact same shape as C. Now you can pull A and B out of context manager. So since you saved two things here, context.save tensors will give you two things back in the same order. So it'll be A and B. Now you want to calculate the gradients of the output with respect to each input. And for addition, basically, I don't know if I need to explain this thoroughly, but for the simple scalar case where A plus B equals C, and these are all scalars, then the gradient of C with respect to A is simply 1, and the gradient of C with respect to B is simply 1 as well. Now, if we extend that to the matrix case, where this is a matrix with more than one number, the gradient of C with respect to every single element in A ends up just being a matrix full of ones. And you can kind of think of this like, since every element in A was added once, its contribution to C is 1 as well. And it's sometimes easy to think about gradients in context of influence, blame, or like how it affected the final result. So what we want grad A to be is a matrix full of ones of the same shape as A. And that's what we would, well, I misspoke. What we want the gradient derivative of C with respect to A is a matrix full of ones with the same shape as A. And that's what we have here. And notice that we only know A shape here because we pulled it out of the saved tensors that we saved here. And then we multiply it with grad output.data because the gradient of the loss or whatever with respect to A is derivative of loss with respect to C, which is grad output here, times derivative of C with respect to A, which is the matrix full of ones. So we just do element-wise multiplication here to get grad A, and then we do that we do the same thing for grad B. And then since this is all computed in NumPy, we want to return tensors, so we just convert it to tensors and return it here. So that's basically the overview of the add function. The subtract function will be very similar. Instead of A plus B, you'll need to do A minus B. And then there are only like a couple places, maybe 2 or 3 things you need to change for subtract. And multiplication is a little more different, but I'm sure you can figure out if you follow the same format. That's it for addition. Jacob, did you want me to do anything further?
No, I think that's good for now. You have any questions? So I guess I will field a couple of these. Sharing screen.
Should I just go through? I can just go through the chat and see.
Yeah, that might be helpful too. And in fact, yeah, I might just move on to the next content because we have a lot of stuff, and hopefully the chat will cover it. If not, my dad is calling me. Sorry, Dad. I just hung up on my dad. But anyway, we're gonna, if you guys have any remaining questions, just post on Piazza about the stuff if we move forward. But yeah, so looking at the write-up now, you have the operations. Again, so divide and multiply. So all of these operations, including add, are element-wise. We're keeping things simple for now. And a really big hint with these is that element-wise operations, the derivative of those are very, very similar to like scalar versions of these. Like, you know, if I gave you a function f is equal to x plus y, you took the derivative of that. The derivative of that thing, or of that function with respect to x and y would be very, very similar to what the matrix derivative is. So massive, giant hint. Please just remember what you've used in previous calc. Yeah. So Autograd engine, we've talked about this a lot. People have been asking about function.apply. We've covered that at least part way. Post in the chat if you need any more help with that. But basically the main idea here is once you get all of this stuff running up until here, you should be able to implement the network components and have them for the most part work. You will have to implement some more operations yourself, like so some more things that are similar to this. And in fact, that is going to get challenging. And oh my God, we're approaching the linear, I just realized. But yeah, so basically by this point, you should be able to like add, subtract, multiply the same size tensors and be able to make it work. So now for question 2, this is coding components of a MLP, which is a multi-layer perceptron, basically just like linear layers and friends, like basically that family of stuff. And so yeah, this is a really big note. Please read what we highlight on these things. I saw a couple of people ask the same question. Do we need to implement your own operations and functions? Yes, if you need them, implement them. If you don't need them, you don't need to implement them, is pretty much all I'll say. We have given you some freebies, I believe things like log, reshape we gave you guys, just to reduce some stress. But yeah, that is the gist of that. So linear layer, and so, okay. So sequential, hopefully the sequential is not too confusing. If sequential is confusing, post in the chat, but hopefully it's not. In linear layer, yeah, you're completing linear.forward. This will require implementing matrix operations in nn/functional.py. And we ask you guys to look here and see, I'm pretty much circling it, what that operation is. But one really big note as well is you guys will have to implement broadcasting for addition. If you guys don't know what broadcasting is, watch Recitation 2. That should give you guys a pretty clear explanation of what it is. We also give a really big hint about unbroadcasting. We did have somebody ask if we could provide a visualization of unbroadcasting, and I was having a really hard time thinking of how to visualize it without giving you pretty much what the answer is. So work at it a little bit longer. If it doesn't work, then maybe in the next couple of days, we'll like post some more detailed information about unbroadcasting. But yeah, the hint that we gave you guys about summing is that is so close to the answer. It's very, very close to the answer. So just put some more thought into that, and hopefully it'll make sense. But when you implement a linear layer, it's basically just the foundation of the network. One thing, you need to implement unbroadcasting for addition auto matrix operations. So unbroadcasting, that function that we recommend you implement, that would be useful for pretty much any sort of broadcasting operation. And so I think a lot of matrix operations have broadcasting implicitly built in. Like for any time that that happens, you can unbroadcast probably. I think that's true, and actually have it work. So just a note. Yeah, there's a bunch of stuff we can cover. I'm just going to move on. ReLU, hopefully this isn't too confusing. Yeah, that's all I'll say about that. And stochastic gradient descent. Again, someone had that really good question earlier about, you know, because this is happening after the computational graph, you don't want to be adding to it. And so you'll just pull the data from the tensors and then work with those instead. And that's how you'll actually do it. Hopefully this shouldn't be too confusing. I think people usually get by it pretty fast. Not too many problems. Can people explain the structure of the param object? Is there a param object? So there is a parameter object in the actual torch, but I believe we don't have one implemented in our MyTorch implementation. We just have tensors, but usually the parameter objects in the actual torch are like wrappers around tensors. What is self.params called? Where would that be held? Is that in linear? Params. I have no idea what that is. Okay. Sorry, I gotcha. Okay, and then optimizer. Right. So this is a good question. This will be relevant for homework 1 part 2 as well, is what is this params thing that we provide the optimizer? And in fact, I just realized I didn't write code for that. I mean, I didn't write method comments. But yeah, so this should be the parameters of the network. If you have any sort of network components that inherits from module, if you type, you know, object name dot parameters and then open close bracket, it'll return the dictionary of the network parameters. That goes into here. And what happens is the optimizer will basically modify those network components. Yeah, so hopefully that answers that question. That's a good question, yeah. How to test question 3? Sandbox does not test this. You may have to implement that. In fact, I think we asked you to implement more functions in Sandbox. And backward functional operation classes to kind of grade both inputs and B if one of them is and blah, blah, blah. We will not be computed as gradient. How do we handle that in the operation backward function? That is a doozy of a question. Let's see. Both inputs and B. That's a long question. I'm not sure how to interpret that. And maybe ask them Piazza or maybe a TA answer it. Oh, David just did it. Perfect. All right, so that brings us to batch norm. So I know people wanted to cover this, and yes, this is a little bit confusing. So one note is we did spot, so technically there were no errors, but there were things a little bit confusing in the write-up in the sense that over here in the updated write-up, we swapped the alpha and 1 minus alpha term. This is now the updated write-up. So this is where the 1 minus alpha term is. 1 minus alpha is momentum. Right? So I believe there's an object, and please correct me if I'm wrong, other people, but no, that's not it. There's batch norm. There's an object called self.momentum right over here. Wait, no, that's not right. Oh, yeah, that is right. Yeah, yeah. There's an object called self.momentum. That term is 1 minus alpha. Yeah. So just so you guys know, so these were swapped before. The reasoning for that is technically in the original paper, they used, alpha as 1 minus alpha, and then Torch like sort of swapped the terms, and so that's what we're following now. So yeah, just make sure that you have the updated write-up so you can implement this correctly. Did anyone else have any questions about batch norm? I know people asked about this. Hopefully the explanation of batch norm in the appendix makes things clearer. But yeah, I'm not seeing any questions or people raising hands, so I'm going to assume it's okay for now. Do we need backprop for batch norm and activation? So if you've implemented all the operations backwards and you're not implementing any new operations, then you won't have to implement a backward explicitly for batch norm. But if you would prefer to implement your own backward for batch norm and treat it as like, a new subclass of function, you're perfectly free to. But that does defeat the purpose of Autograd. So I would recommend not doing that. But, it's up to you. Okay. So I will continue moving on. If no other questions. One big note. What I've noticed in office hours and other places is people are forgetting that batch norm works differently when isTrain is true and when isTrain is false. So you'll have to implement an if statement that looks at this this variable and then determines what to do based off of that. That's the hint I'm going to give you now. So I'm sure people are wondering, oh, what do we have to check for? You just intuit it, figure it out once you get to that part. But yeah, so cross entropy loss. Cross entropy loss is going to be tough. Is the unfortunate news. Can I explain what the gamma and beta are? Someone asked a question about batch norm. Can I explain what gamma and beta are? Yeah, actually, can one of the TAs explain that? I'm actually not 100% confident. I should know this. I read the paper a bunch of times when I was working on this. But yeah, if you ask that in Piazza, we'll answer that question. But yeah, okay. So cross entropy loss, yeah, this is going to be a little bit annoying. Again, in this case, if you would prefer to implement your own backward for like a new subclass of cross entropy loss, you're perfectly free to. In fact, it's possible that that might be easier because the derivative of cross entropy loss is quite simple. I'm not sure what the actual Torch does, but yeah, it's up to you. Because it's, at least in our implementation, we've implemented it in a way where you don't actually need to implement any more subclasses of function. So it's certainly possible. But yeah. And then finally is momentum. It's a really simple modification of SGD. So don't overthink it too much. It should be a pretty quick pass, hopefully. Okay, so that'll bring us to MNIST. Is Antti here? Antti may or may not be here. Antti's been very busy lately. Okay. Yeah, so I'll just talk about, I'll continue talking about MNIST. So MNIST, so this is another, this is a particular section of the write-up where we've made a bunch of updates. This is the only section where there's an update that might affect the code. It's an update to the write-up. And so you'll want to re-download the write-up for this section pretty much explicitly. But it doesn't seem like too many people were affected by it, and the people who were affected by it managed to get past it pretty quick. So hopefully that shouldn't affect too many people. But yeah, I'll explain those when I get to them. So one thing, okay, so I guess maybe looking at the code will be clearer. So in MNIST, we're basically asking you to implement these 3 methods. This is pretty much all you'll need to implement for MNIST. Oh yeah, and the make sure implement packages you needed. That's pretty straightforward. But yeah, in this method over here, MNIST, you're basically creating all the objects that you need to run this code. And then you call the training routine, which is over here. And then the output of the training routine is a list of accuracies that you get during the validation phase, and you just return that. And what the autograder will do is it'll handle creating a graph that sort of plots the accuracies over the course of the training. So that's pretty much it. One thing that we did fix is make sure to set LR, the learning rate of your optimizer, to 0.1. We totally forgot to mention that. But yeah, this is important for your network to converge quickly, because the illustration that we have in the write-up over here, this was done with LR equals to 0.1. Your network still will train if you set it slower to the default. I think it's 0.01. Yeah, the default is 0.001, okay. Yeah, it still will learn, but that is pretty slow. But yeah, is this right? I think, okay, I'll check that in Torch later. But yeah, so just a note, just make sure you set that. Okay, cool. And so continuing on with MNIST, yeah, this network architecture should be straightforward. Just create those objects, call train. There's an explanation of batching over here. We had a lot of questions about batches and what they were supposed to be used for and what they meant. There's an explanation of it briefly here and also in cross entropy loss. Let us know if something's not clear. We'll talk about that. But yeah. And then, okay, so people are asking questions. Oh, is write-up not updated on the website? I don't know. Darn it, I forgot to push the latest write-up. Yeah, that's a good question, thank you. So yeah, I will update the latest write-up in a second. And then I'll also make the change log later, by the way, so we'll figure that out. So yeah, talking about train, these things are already set, should be fairly straightforward. This pseudocode is correct. We did make one change. This was the critical change. We need to reactivate train mode right after validation. I think this is one of the best places to do it, because what was happening before is we just told people to activate train mode up here, and then it would go to validate mode, or it would go to testing mode, and then it would never exit testing mode because it's just still within this for loop. And so that's no good. So we need to reset it over here. Make sure to do that. Did the code get updated any chance? No, none of the code ever changed. We just had some comments that we updated, but they were pretty minor updates, I would say. So yeah, and then, so that would be train. It's fairly straightforward. This code, like this pseudocode, is essentially all that you need to do. It'll maybe be like 2 to 3 lines longer, but not much longer, if at all. And so, yeah, and that brings us to validate. So again, hopefully you guys understand the difference between training, testing, and validating. Those are very, very important in machine learning in general. If you don't understand the difference between those terms, we've provided a link to a Wikipedia article. Like, that is a very, very good article. Also, just in general, Wikipedia is excellent for math and CS in general. Like, when writing the write-up for this and also when working on this assignment, I spent many dozens of hours just on Wikipedia reading articles. So I strongly recommend you guys do the same thing, because you can learn a lot from there. Obviously, it's not always correct, but it's very, very often correct for those parts. So yeah, just a note. All right, so validate, basically implementing the validation phase. There was another change here where we had it running for like n epochs, like epoch epochs, and you don't need to do that for validate, you just need to do it once. And so that was just a mistake when we had copied and pasted this code over. So just to know, you just need this one for loop in here. You validate once, and then you get the accuracy and you return that. So that's pretty much all you'll need for that. There was a couple of problems that people had with generating the final submission with like the image and getting it to zip up. That usually, from what I saw, had to do with like operating systems or which command console you're using. So just like, if something happens to break here, like, strong recommendation is just Google it first. Because if it's an operating system problem, chances are very, very good the TAs will also have to Google it. And so I noticed, like, sometimes people post debugging questions where they ask, like, oh, how do I debug this? And then the exact problem itself is written in the error statement. It's just that you didn't look at what the error statement was. So if you actually just copy and paste the error statement exactly as is verbatim into Google, like, very often, like 8 out of 10 times, it'll give you a very relevant answer and tell you what the problem is and how to fix it. So please, strong recommendation to do that for whatever the issue is. But yeah, if it's math and other stuff, then it's probably on the side of the TAs. So someone asked a question for the deadlines. Oh shoot, I didn't even go over the schedule.
Sorry, it
Oh,
was
yeah.
planned by Zihao, but I guess like he unreleased it. But okay, he's back. Sorry.
Yeah. Just about the batch norm. As long as we need to maybe decompose the batch norm function into several other functions, and the batch norm is only we only concerned with 1D. These other functions are actually we only concern 1D too, because those functions may be needed in the future, like the sum or the mean function.
Oh, are you asking if you need to implement operations?
Yeah, I need to implement those operations. Do we need to concern like for 2D dimensions? We also need to concern how to
So this is
backward for those.
covered by the FAQ. Yeah, just look at the homework 1.1 FAQ is essentially all I'll say. But yeah, the short answer is it's up to you. But yeah.
Okay.
So yep, so plotting and submission, I covered this part. Again, yeah, so your plot doesn't need to match this plot exactly. It probably will, like, be very, very close to this if you get the LR to the same rate. But yeah, this is how it generally looks. And then when you basically run, I believe it's create tarball later on, as long as the image is, I believe it's going to be in this folder. I'm not quite sure. As long as the image is where exactly where it is when it was generated, it'll be included in the handout. And then when you submit to Autograd, or when you select Autolab, the TAs will manually go through later and grade it. So that's pretty much all there is for that. Oh yeah, so I forgot to mention, the appendix is really important. And you know, you're probably going to end up reading most of it throughout the course of this homework. You may not implement all of it, but yeah, like, oops. Appendix A is something that you're probably going to read all of. It's pretty useful. Appendix B, you're also probably going to read all of this as well. You're going to read all of that. You're going to read all of this. This one you may or may not read. What the key point of this is this, is this right here. This is the derivative, like, so the backward of cross entropy loss. It looks ridiculously simple. It is very, very simple. The thing is with this though, is if you just implement this as is, you're not going to get the correct answer, because I think this version of cross entropy loss assumes like one observation. Remember that you have to do this over a batch of operations. And so if we're doing like a mean sort of averaging for the cross entropy loss, then you have to also here do something with n, is what I will say. So this sentence says, remember you've averaged over the batch during the softmax by dividing by n. You have to undo that during the backward somehow in here. So that's what I will say. But batch norm, hopefully this explanation is clear. Yeah, this is a good conceptual explanation, I think. And then over here is basically, it's very similar to that above description, except with a little bit more conceptual detail. One change we made to the write-up is we added this back in. This was missing. But I mean, that formula was above anyway. So, but yeah. Yeah, that's basically the write-up. So one last, I guess, maybe really quickly, I will go to the course website and we'll walk through the schedule coming up, because I know people are kind of concerned about that. And then after that, we'll take questions in general about homework 1 part 1. So again, keep in mind that this is going to be pretty small. I just want to, okay. So keep in mind that there's going to be a lecture on Monday, Wednesday, Friday. Monday and Wednesday, like as normal next week. So you'll have to go to those, and then also pay attention to those as well. Yep, so one person I saw, people were asking about the early deadline for homework 1 part 2. This is the homework schedule over here. Basically for this, all you need to do is submit the sample submission. Like, ideally you should submit a full, like, completed version of homework 1 part 2, but I guess if you're worried, you can just submit the sample submission. It'll give you a very poor result. But as long as you have something in, you will pass this part. That's what I'm saying. All right, that's what the advice is. The point of this is, like, the reason that we have this in here is just so that you're thinking about this, and so it doesn't take you by surprise at the end. This gets you to start sweating a little bit and say, oh man, I need to start on this. So that's the point of that. Um, I would just strongly recommend, if you want to have peace of mind, just after this session right now, like just go and just submit it, like the sample submission, just once. That way you won't have to, wake up 1 hour before the deadline on this point and go, oh my God, I need to make the sample submission and then do that, which I actually did twice last semester. So don't do that like me. Oh yeah, and then also we canceled quiz 2. There's going to be a quiz next weekend. And these are the deadlines. Just a note, homework 1 part 1 is due on the exact same day that the homework 1 part 2 on time deadline is. And so does it list the late deadline? I don't know if it does. Wait, and other TAs, what was the policy for the submitting after the on time deadline? If you can remind me.
Wait, what did you say? The on-time deadline for what?
What was the policy for like submitting after the on-time deadline?
For part 2?
Yeah, for part 2.
They just use Slack days.
Okay. And did they have 7? Was that the policy?
I think it's still 7.
Okay, cool. Yeah. So I recommend, like, because you won't have Slack for homework 1 part 1, like for the part 1s, I'd recommend just submitting this, like prioritizing getting this in on time. Also keep in mind that homework 1 part 2 takes a lot of time to train. So keeping that in mind, maybe what you could do is you can get homework 1 part 2 training ready and then have that training in the background while you finish homework 1 part 1. It's up to you, like what your personality is and what you like to do. So just keep that in mind. Yeah, hopefully that should get you in by this point. What I'll say. So the ordering that you want to do this stuff depends on you. But a strong recommendation is actually just attend all the lectures or watch the lectures on the exact same day that they've been done. Because once you get behind, DL lectures are dense. I'm sure you've noticed. Each slide is packed. If you try to cram like 400 slides worth of slides in like 4 hours, you will not be able to do it and learn anything adequately. You need to space things out. So like watch it on the same day that you have the lectures. Is a strong recommendation. And any other tips from TAs on what to do, scheduling?
I mentioned this thoroughly in my recitation, but when you start doing part 2, make sure you save exactly what you did for every single training run, or it gets really, really sad after 8 hours and then something goes wrong and then you have no clue how to reproduce the result. And save your model checkpoint files. And to re-emphasize, please Google things before you post on Piazza. Otherwise, it's like there's some questions that can't be answered by Google, and we would like to answer those questions the most. But if we get swamped by Googleable questions, then it's just not efficient.
Yeah, just that's a really good point. Just a hint in general is like the Torch docs are very, very good. Like they're some of my favorite online documentations for things. Just have this bookmarked. I pretty much had it open constantly the entire semester. Like just have this open and refer to it constantly because you're going to need it for those homework 1 part 1 and homework 1 part 2. For pretty much every homework part 1 and part 2, you're going to need it. So just this is something to keep in mind. Yeah, so just going back and looking at it. That's pretty much all I had on this. I guess we could start taking wildcard questions unless another TA has a suggestion on what we can look at. Okay. All right, yeah, so I guess if you guys have any questions, raise your hand and we'll start taking questions. I don't know what the participant was.
Probably start taking questions from chat directly.
Okay. Am I still sharing my screen, by the way?
Yeah.
Okay, cool. Oh, okay, there it is. All right, so participants. So I see someone's raised their hand. Shreefa, you want to speak?
Yeah, hi. I had a question regarding homework 1 part 2. So do we need to optimize training time in that as well?
Someone want to field this question?
Did she ask about training times?
Yeah, she asked if you need to optimize training times during homework 1 part 2, if that's required.
Trudy, could you clarify what you mean by optimized training times?
I mean, I am trying to optimize my data loader, and I don't know to what extent should I optimize it, because like it works fine with AWS, but when I work it on Google Colab, it starts crashing, like the RAM starts crashing. So I don't know if we need to optimize in terms of RAM usage, time, resource usage, memory, like all those things.
So you don't actually upload your model to Caradle, you just upload the submission file. So
Okay.
and the submission file takes a constant amount of time for everyone because it has like the same number of rows that you submit. So I don't think that should be an issue, but it should be an issue for you because you would be training it for a longer time if your model is not optimized.
Okay, so it's just like we don't need to submit code for homework 1 part 2.
You do, but that's after a week of the submission deadline. So suppose 27th is the submission deadline, on-time submission deadline for homework 1 P2. And after a week, you clean your code, make it nice and format it. And you also submit like a write-up about the architecture, and that goes on Autolab. But we don't really like run the code, but we do check for plagiarism.
I see, I see. Okay, thank you.
Someone's asking, what is a ballpark figure for expected accuracy for part 2? We're going to release the benchmarks for I guess grades, and that's going to be pretty soon, right? Or is that the on-time deadline?
We released it on the early deadline for
Okay.
part 2.
Yeah, so that'll be in 4 days. For now, I would, I guess, focus on trying to get the code up and then finishing as much as part 1 as possible. But yeah, oh, Tony just answered. It's around 70 plus and minus 5 is the answer.
Could be 75, could be 65. We'll see.
Hello Kitty menace is affecting your guys' scores.
Other questions?
Yeah, I found that we don't need to do quiz 2 in the course website, but it's still in our canvas. Do we need to do it?
So we will figure out a way to include some questions or new questions from lecture 3 in quiz 3. So you could expect 13 quizzes in total and still 2 will be dropped. I know that was a recurring question on Piazza.
Okay, thanks.
Yep. Any more questions? Yeah, it seems like we've answered a lot of the questions.
Don't jinx it, please.
I guess it's probably like just general apprehension about the homeworks instead of specific concerns, which is extremely relatable. Yeah. Yeah, if that's the case, then I think we might start calling it because it's been an hour and 20 minutes or so. So yeah. Let us know if you have any questions, post in the FAQs. Thank you guys for coming, and hopefully this was helpful. And also thank you so much to the other TAs and everybody. Yeah.
And Jacob, we're so proud of you.
Oh, what's that?
I said, we're so proud of you.
Oh.